Hello all, welcome back to nuclear chemistry, nuclear physics. Never remember. It's basically the same, would happen in the same hallway, in the same building, at the same institution. Anyway, welcome back. I want to pick up where we left off with 19.2. Hopefully you didn't have any trouble with that OPG assignment, and I'm hoping that you may have found it somewhat interesting to see where electricity comes from, and to again just be looking at where, again, just another area of huge area for careers and for future study. What I want to do today is I want to look at a discovery that was made beginning of the 20th century, actually the end of the 19th century, by a French physicist named Henri Becquerel. And he had basically really discovered radioactivity. He had left some photographic film, I don't think unintentionally, near a chunk of uranium, and when he did and he came back, he found the photographic film had been exposed, even though no light had been where the chunk of uranium had been sitting. You could see that it had given off emissions. The radioactive photographic film was actually encased in a very thick sleeve of cardboard, so no light could get through it. So the film, remember, is photosensitive. So at the end of the day, what he'd found were rays of energy that were traveling from the chunk of uranium, traveling through the thick cardboard, through the film, and then ultimately probably coming through the back end, the other side of the casing that the film was in, and probably was very dangerous. And again, not really realizing what exactly he was discovering or playing with or dealing with, he had really ultimately discovered a key to understanding all of matter, which was the basis of the nucleus. Now, what we're going to talk about in this section here was a huge part of the discoveries in the early part, the first half of the 20th century, when we were looking at trying to understand what happens, what is the atom made of. And we all think about protons, neutrons, and electrons. We think about Bohr diagrams. But there's much more to it. That's just kind of scratching the surface. And I think I didn't even really get the gist of it all until I was quite late into my post-secondary studies. I want to talk today about really one type of nuclear reaction. There's basically two broad categories of nuclear reactions. A nuclear reaction is a reaction in which the nucleus is changed. Right, that's what a nuclear reaction is. The nucleus is changed. Now, at the end of the day, remember the nucleus tells us a lot about the atom. It tells us how many protons and how many neutrons. The number of protons tell me what element it is, and the number of neutrons tell me what the mass of the particle of the nucleus or of the atom. Now, if I start messing with the structure of that nucleus, then I start changing the properties of that atom, and maybe drastically. As you're going to see in a few minutes, I might even change the atom into a different type of atom. So what we've talked about in the past are chemical reactions. Right? If you take 3U chemistry, you learn about your basic chemical reactions. Right? We learn that in a basic chemical reaction, whatever atoms we have in the reactants have to be present in the products, because atoms cannot be created or destroyed. Right, whatever atoms we have in the system at the beginning of the reaction have to be there at the end. Okay, nuclear reactions, that's not the case. Right, if you look at the example I've got here, the first example shows an atom of plutonium, which is element 94 on the periodic table, starting off in my test tube, and when I'm done, plutonium is gone, and I now have uranium. Think, no, you can't turn an atom into another atom. Well, in a nuclear change, in a nuclear reaction, we can actually change elements into other elements. Notice what's being given off here. The other product is a helium atom. Right? Helium is number 2 on the periodic table and has a mass of 4 because it has 2 neutrons and 2 protons. Now, if I keep moving down here, you can also see another example is where I'm going to start with an atom of hydrogen. It's radioactive. It's heavy hydrogen. Hydrogen's got a mass of 3. Remember, hydrogen usually has a mass of 1 and 1 proton, which means there are no neutrons in a hydrogen atom. This hydrogen atom is a heavy hydrogen atom. It contains one proton and 2 neutrons. And what's ultimately going to happen is once this reaction is done, I'm going to have a helium atom. You think, well, that's a good trick. You start with a hydrogen atom, you turn it into a helium atom. There's got to be a use for that. There's got to be a way that we can use that for something productive. And again, notice what the other product is here, is an electron, right? So when the hydrogen is turned into a helium, I'm also going to release an electron. Now, I'm going to keep on scrolling up here. So when I think about the nucleus, right, and what I understand about the nucleus today is I know that the nucleus contains 2 particles, right? It contains protons and it contains neutrons, right? And what I do know is that the nucleus as we know it should not exist because it's a mass of neutral particles and positive particles, and the positive particles don't like the other positive particles because we know that like charges repel, and because of that the nucleus should basically explode. It should not stay together the way it is, right? I understand about the electrons in an atom, right? The electrons are attracted to the opposite charge in the nucleus, and there's a force of attraction holding the electrons in, but what was holding the protons in the nucleus with the neutrons? And it turns out the neutrons have a lot to do with holding those protons together, right? So 2 forces going on here within the nucleus of an atom, right? One is the electrostatic force. It's a force of repulsion between positives and positives. The other one is a force that we discovered called the strong nuclear force. Right, this is the force that basically holds the nucleons together. And nucleons are protons and neutrons. Right, nucleons are the particles in the nucleus. Right, protons and neutrons. So those are the nucleons, and what holds them in the nucleus is this new force called the strong nuclear force. Not so new now, new to us. Now that being the case, I've got these 2 things going on. One is the force of attraction, which is holding these particles together, pulling them together because of the interaction with the neutrons, and one is the force of repulsion because of the electrostatic force of repulsion between the positives that are happening within the nucleus. Now what I need to have some type of balance between the repulsion that's going on in the nucleus and the attraction that's going on within the nucleus. If I have too much of either, right, it's going to be a problem. All right, and you think, well, really, how can I have too much attraction? If I have too much attraction, that doesn't sound like a problem. I have a problem if there's not enough attraction, because the whole thing could really explode. But as we're going to see in a few minutes, it can be a real problem for an atom if they've got too many neutrons. Right, too many protons is bad, but so is too many neutrons. So I've got to have the right balance between the nucleons that are present within that nucleus. Now, typically, the magic number is around 82. So for atoms that have an atomic number which is greater than 80, I'd say as a good generalization, those particles typically tend to not have enough of the strong nuclear force that they need to hold them together. The reason for that, there's not enough nuclear force because they need more neutrons to balance the force of repulsion. So what's going to happen here, if I look at a uranium-236 atom, if I look at a uranium-236 atom, uranium is 92 on the periodic table, so it has 92 protons, and the other 236 minus 92, we know from last night's homework, is the number of neutrons, and it's 144. Right, so there's a lot of neutrons present here. There's not the appropriate amount of balance between the two. Right, so what I need to happen here is I need to change what's present within the nucleus. Okay, and the way that that changes is based upon the type of what's called decay. When the nucleus splits apart, it splits apart by giving away particles within the nucleus, and we're going to see, well, what does that mean? Giving away protons, giving away neutrons. How can we give away protons or neutrons? They're stuck in the nucleus. Here we're going to look at how we can split a nucleus apart, okay, and in doing so, try to make the nucleus more balanced. Right, so that's the whole goal here in everything that I'm going to talk about in the next 15 minutes or so, is how do we break the nucleus, change the nucleus, often by taking particles out of the nucleus, and in doing so, I'm going to try to balance those attractive and repulsive forces that are going on within the nucleus. So we're going to talk about three kinds of, so what we call that when the nucleus splits apart, we say that the nucleus is decaying. Okay, decaying. And as we're going to see in a minute, that usually comes with the release of radiation energy in the form of radiation, radiant energy, electromagnetic energy like we've seen before, and that radiation can be quite dangerous, as we're going to see. So if we keep moving up here, the most common type of decay, right, typically happens for very large nuclei. It's called alpha decay. It's called alpha decay because it was the first one discovered, and we discovered that the nucleus of the atom was being changed. It was being changed in a way such that the nucleus lost a particle that contained 2 protons. So if a nucleus loses 2 protons, that means its atomic number goes down by 2. So we'll just use lead here for an example. So lead is number 82 on the periodic table, and when this reaction was done, it had turned into a mercury atom. Again, this is kind of breaking all the rules of everything that we've learned about chemistry up until this point, so don't tell Ms. Orban. We're going to change one element into another element. You think, okay, well that's okay. How does 2 protons get ejected from the nucleus of an atom? Well, we discovered not only does the atomic number go down, but the mass should go down by 2 also. If I lose 2 protons, I should be losing an atomic mass number of 2 also, because protons have a mass of 2. But it turns out that the mass goes down by 4, right? So the mass going down by 4 means this thing that's been launched out of the nucleus of this lead atom, right, causing it to drop from a mass of 204 to a mass of 200, right? So it's losing 4 nucleons, 2 of which are protons. The other 2 have to be neutrons. So this thing here, this thing here is a particle, right? It's a nucleus. It's an entity that contains 2 protons and 2 neutrons. Now if I think, what do I know about something that has 2 protons and 2 neutrons? Well, that's a helium nucleus, right? Helium is number 2 on the periodic table, and it's got a mass number of 4 because it also contains 2 neutrons. So this particle here, which has been called an alpha particle, alpha being the first particle to be discovered, I would think, is basically a helium nucleus. You think, what about the electrons? Well, we're not talking about the electrons because I'm only worrying about what's going on within the nucleus of this atom, of this lead atom, right? Because this is where the action is, right? The action is not about some electrons that are going to go here or there. The real action is what's happening to the nucleus of this atom. Now, when the nucleus changes, changing the element to a different element, changing the mass to a lighter mass, by creating a whole new element, that's called a transmutation. Right, so a transmutation is the name of all the reactions we're going to see in the next, like I said, 15 minutes or so that involve an element turning into another element. And we're going to see a number of examples of that. So we've just seen the example of lead 204, right? And the reason why lead 204 gave off that helium particle is because it had more neutrons than protons, right? We've already seen that. It's got 122 neutrons and 82 protons. So it's got many more neutrons and protons. So it's going to kick out 2 protons and 2 neutrons to lower the number of both. Right? And what that does is it tends to bring some stability to the nucleus, right, by kicking out that alpha particle. Now, it says, notice that we've got a conservation of mass here and conservation of the number of particles. So if my atomic number is going down from 82 to 80, right, I have to have all 82 accounted for. So there's my other 2. And then if I'm going down from a mass of 204 to 200, I have to account for my missing mass, which is the 4 mass units that are on the helium nucleus. Okay, and then we're going to look at charge as we come out of this, because this nucleus, as it gets kicked out, it's going to basically create a negative ion of that mercury, and then basically the electrons typically will leave the mercury and will be accepted by something else. Okay, but we're not going to worry about the electrons for this discussion. We're going to focus on the protons and the neutrons. So that's alpha decay. So the sample here says write the equation for the alpha decay of radium-226 to a more stable isotope. Okay, so if it's radium is number 88 on the periodic table. Means it has 88 protons, and it has a mass of 226. Okay, it tells me that in the question. Right? If I'm going to alpha decay this thing, I'm going to create my alpha particle, plus I'm going to create another atom now that has 226 minus 4. It's going to have 222 for a mass. And it's going to have atomic number of 86. And none of my styluses are working very well here. 86, it turns out, has changed to a new element that's called radon, right? And this radon atom, again, has a mass of 222, and it has its atomic number of 86. So I've turned a radium atom into a radon atom by ejecting that alpha particle. Right? And this particle is more stable because I've managed to get rid of some of the positive charge that's within the radon, but I've also got rid of some of the excess neutrons that are also present within that nucleus. Okay, my second type of nuclear decay, so things are going to get a little bit, so that was weird, right? But it's going to get a little stranger yet. Okay, so my second type of decay is called beta decay, and there's 2 kinds of beta decay. Okay, so in beta decay, what's happening is we're trying to change the balance of protons to neutrons. We're going to do that by, okay, ready for this? Turning a proton into a neutron, or turning a neutron into a proton. So those are our 2 possibilities here now. So inside the nucleus of this particle, I'm going to convert nucleons, right? Protons to neutrons or neutrons to protons. You think, how do I turn a particle into something that it's not? And again, we'll find out a little bit more about that in 4U physics. For now, we're just going to look at the process itself. So in both of these cases, again, remember it's decay, so I have to give off something from the nucleus. Before it was an alpha particle, which was a helium nucleus. Now I'm going to give off a beta particle. Now there's two ways this can happen, right? One possibility is that the nucleus is going to have beta negative decay, and the particle that's going to be ejected from the nucleus is an electron. Wait, there's no electrons in the nucleus. How can we have electrons ejected from a nucleus if the nucleus doesn't contain any electrons? Well, it turns out that in this case, if there are too many neutrons for the number of protons in the nucleus, what can happen is to stabilize the nucleus, the atom can convert the neutron here into a proton and an electron. So this happens within the nucleus of the atom, right? This neutral particle will get converted into a positive particle. Think, well, how did something become positive? Well, it can't on its own. The charge has to balance, right? I have to have that that mass balance and charge balance. I know that I had a mass over here of 1 with no protons. Now I have a mass of 1, which is a proton, so my mass hasn't changed, and I'm going to kick out the electron. But if I've created a positive particle, I have to also have created a negative particle so that these two have the same charge as the neutron had to begin with. Right? So my charge has to balance here on the left and on the right. And notice what's happening is I'm taking a neutron and converting it to a proton. So what that's meaning is the atomic number of the element is going to change. Atomic number is going to go up by 1. I created another proton. Right? If I change the atomic number, I'm going to change the element again. Transmutation. I'm creating a different element. So the overall formula for this reaction is here, where it says an element with a mass of A will change into a different element that has mass A. How do I know it's a different element? Because originally it had Z protons and now it has an extra proton. Right? But its mass hasn't changed because remember the mass of the neutron and proton are almost the same. And I'm going to kick out that little electron and it's going to get ejected out of the atom. Right? Now, an example of that would be the one that we saw earlier, which was the reaction whereby the hydrogen atom, which was hydrogen 3, is going to react and to become a helium-3. You think, well, hang on, helium's supposed to be atomic number 2, helium, and supposed to have a mass of 4, but there, again, remember the number that we see on the periodic table represents the average of all the different isotopes based on their relative abundance. So what I've got here is a helium atom being produced, right, because it's now converted where originally it had over here, here it has 1 proton and 2 neutrons, which means it's 3 and 1. Now I'm going to have 2 protons and 1 neutron, right? Because I've taken one of the neutrons from here, and now I only have 1 neutron left. I've taken that neutron and turned it into a proton by ejecting that electron. So there's my beta there's my beta particle right there. Right, the beta particle, it's called a beta negative particle. Right, the beta negative particle, I was seeing it up here, and the beta negative particle is the electron, and it's going to get ejected from the nucleus of the atom. Okay, so another example of that is when carbon-14 decays by beta negative decay. Okay, so here is my carbon-14. It has 6 protons and 8 neutrons. 6 protons plus 8 neutrons. Right, atomic number is 6, mass is 14. Now I'm going to take one of the neutrons, I'm going to convert it into a proton. So I will now have 7 neutrons and 7 protons. That's what I have here. 7 neutrons and 7 protons. In converting the neutron into the proton, as we saw up here, I also am going to generate that electron, that beta negative particle, and it's going to get ejected from the nucleus here. So carbon atom is going to get converted to a nitrogen atom, and in the process we're going to launch out a beta negative particle. So that's beta negative decay. Okay, so hopefully I'm not going to cause you to lose any sleep here tonight. This is distant. It's far from anything that we've seen or done to this point in chemistry or physics. Okay, so just hold on to your hats here because things are going to get a little bit stranger yet. Okay, you're probably seeing that red thing there and saying, okay, positive electrons. This is really going downhill fast. My other type of beta decay is when a particle gets launched out of the nucleus called a positron. A positron can get launched out of the nucleus, and a positron is a positive electron. Looks like an electron, has the same mass as an electron, has the same amount of charge as an electron, except instead of having negative charge, it has positive charge. Positive electrons. Okay, so How is this possible? Because it turns out that for every particle in the universe, there is an antiparticle. There's an opposite particle. This is part of our understanding of matter in the universe being made up of particles and antiparticles. So the antiparticle for any particle has the same mass as the particle that it's opposite to, right? But it will have the opposite property, for our purposes, the opposite charge. Okay, so if I could measure the amount of charge on an electron, 1.6 times 10 to the negative 19 coulombs, and that's negative, and compared it to the amount of charge on a positron, the positron has the same mass as the electron. It has the same amount of charge, 1.6 times 10 to the negative 19 coulombs, but is positive. Okay, so we now have, positive electrons. Okay, and again, if you go on to take senior physics, you will get into some of these antiparticles, antimatter particles, and it gets interesting, but you really got to have an open mind because it goes against everything that we already think we know about matter. Everything you thought you knew until about 3 minutes ago is probably all upside down now. So, just like that electron, right? Beta negative emission. I'm throwing electrons out of the nucleus. Again, there's no electrons in the nucleus. Well, I'm sure if there are no electrons in the nucleus, there's definitely got to be no positrons in the nucleus either. Well, it turns out that if I take what's going to happen here, this occurs, right, whenever I've got too many protons in the nucleus for the number of neutrons. Think, well, how am I going to deal with this? Well, the proton gets converted into a neutron. Okay, so that's the goal of the nucleus here. I've got too many protons, not enough neutrons to balance it. My nucleus is really unstable. I need to balance this somehow. Right, I've got to get rid of the protons or find some neutrons somewhere. Oh, let's just convert a proton into a neutron. So if I do that, right, you can see that my proton here is going to get converted into a neutron. Remember, they have the same amount of mass, but the proton has positive charge, the neutron has none. So if I add up the mass on this side, I have 1 on the left and 1 plus 0 on the right. If I add up the charge on the left, I have a plus 1 on the left, and I have 0 for the neutron, telling me that this electron that has no mass, or very little mass, is positive. Right? That's called a beta positive particle. Right? And like I said, it happens when there are not enough neutrons there for the number of protons. Now what's going to happen this time, unlike before, where the atomic number went up by 1 because I created a proton, now I'm turning a proton into a neutron, so my atomic number is going to go down by 1. So again, it's a transmutation because I'm changing the number of protons. In other words, I'm changing the element into a new element. So my general formula for this says any atom that has a mass A and a number of protons Z will ultimately lose one of the protons and convert it to a neutron, so the A doesn't change, mass is the same, but I have to allow for that beta positive particle to be eliminated from the nucleus, right, so that I've got charge balance. An example would be if I start with a carbon 11 atom. Okay, again, 6 protons and 5 neutrons. Again, the atom isn't totally stable this way, and it would be more stable if I could convert one of the protons into a neutron and have 5 protons and 6 neutrons. So it does that, right? But in order to do that, I've got to get rid of the positive charge that was on the proton that we just got rid of. That positive charge gets ejected as a positron. Okay, that positron is my beta positive emission, right? And that's what's going to get kicked out of the nucleus. So I've now got 3 things that can be kicked out of the nucleus, right? One was the alpha particle, a helium nucleus. One is an electron, beta negative emission, and one is a positron, a positive electron, which is a beta positive emission. Okay, hopefully you're still okay. All right, so 3 is the sample here. It says write the equation for the beta decay of bismuth 214 to form a stable isotope. Now, I think it should it should tell me if it's beta positive or beta negative decay. I've got no clues here. Okay, so bismuth 214. So bismuth on the periodic table is, I haven't got my periodic table here. Bismuth is 83. Oh, come on. Bismuth is 83. Right. And it would really need to tell me what kind of decay is happening here. So let's look at a possibility. 208, 209, 210. So I'm going to make up a number here because I don't know what the isotope is. I'm going to make it up as bismuth 210. Actually, I'm going to do the two samples that are in our textbook. Right, that'll be easier. So let's get rid of this sample problem here. And I'm just going to, let me switch to my whiteboard. And we'll look at the sample that's in the textbook on page 639. On the test, which is next week, remember we're doing thermal energy and nuclear energy together on the same test next week. So this one has got radon. This is the sample from page 639. And the first example, A, says I'm going to take a radon, which is, radon is number 86 on the periodic table. And it says it's going to get converted into a polonium atom, which has a mass of 218 and atomic number of 84. Boy, these styli are not working very well today at all. Okay, so 218 and 84 plus something, some emission, whatever the emission is. Okay, and what I'm seeing is the atomic number is changing by 2, going down, right, which could either be some type of beta emission. Oh, but the atomic mass is also changing. So if the atomic mass is going down by 4, oh, this, I see where this is going. This is going to be basically giving off an alpha particle. Right, so I know that this is alpha decay, right, because it's giving off an alpha particle. The B example here says neptunium, which is number 93 on my periodic table. This atom has a mass of 239, and it's going to get converted into something by giving off a beta negative particle. It's giving off this particle, and it's going to get converted into something new. The question is, what is the new thing? Now notice that if it's giving off an electron, it's going to be a beta emission, which means the number of nucleons doesn't change. So this new thing is still going to have a mass of 239. It's still going to have a mass of 239, but I'm also going to have, if I've given off negative, means I've also created positive. Means I've converted one of my neutrons into a proton, so I now have 94 protons inside the nucleus, and the element that contains 94 protons is plutonium. Okay, so when I have beta negative decay of a Neptune 239 particle, I'm going to end up, I'm going to convert it into a plutonium 239 particle. All right, so there's two types of, first alpha and then beta negative emission. All right, let's go back to nuclear power here, nuclear energy, and let's just finish up. Okay, our last type of emission is energy. It's radiant energy called gamma decay. So in the Latin alphabet, alpha is first, beta is second, and gamma is third, ABC actually in that alphabet. So gamma decay is the third type, and gamma decay is basically when energy is being released from the nucleus of an atom. And you think, where could energy come from? Again, that's beyond the scope of this course. We'll get a little bit into some of this when we get into E equals mc squared in about 2 days' time. But for now, we're just going to look at the fact that energy is released. Now, what happened here, and we didn't talk about this before, but when the hydrogen 3 got converted into a helium 3 by beta negative decay, all right, there was a step that we missed. I went straight from here to here, right, where the helium was given off. But there's actually another piece here altogether that needs to be included in this whole thing. So what happens is that neutron gets converted into a proton. So this one proton that I have here, right, will be replaced in the atom by a second proton because one of the neutrons got converted into a proton. So here I have one proton and 2 neutrons, right? 1 proton and 2 neutrons. And here I have 2 protons and 1 neutron. Right? And in doing so, I've created the beta negative emission, which is the electron. Now what happens here in doing so is I change the energy associated with that atom. It now is at a heightened level of energy, right? By making the stable energy, by stabilizing the nucleus, it's got energy that it has to get rid of, that it was using before to hold it together, but now that it's more stable, again, it's like dropping something and it loses gravitational energy. This is going to be the same. It's gained energy by becoming more stable, and that energy we show as that little asterisk that I have up here. Right? And the question is, what happens to this thing now? If I've got this energetic helium, what's it going to do? Well, it's going to give off that energy to become a stable helium 3 atom, nucleus atom. Right? And the energy that comes off is in the way of a gamma radiation. Okay, so there's my gamma wave. Remember, if we think all the way back to the ISU, in the beginning of Chapter 10, we talked about the electromagnetic spectrum. We had radio waves at one end, and we had gamma rays at the other end. They are the shortest wavelength on the electromagnetic spectrum, which means they carry the most energy. Right? They're the most dangerous of all the ones on the electromagnetic spectrum because they carry the most energy. So this is the energy being taken away from this excited helium atom. Okay, so this happens both when we have alpha decay and beta decay. Right? We end up with the nucleus going into this excited state, which means it's got too much energy, and we're going to write it with that little asterisk that we were just showing. Okay, and that energy now is going to be released as a photon, a bundle of gamma radiation. Right? It has no mass, right? 0 and 0. No mass, no charge. And that gamma radiation carries energy with it. Now, when I think about the characteristics of these 4 different types of radioactive emissions, they will all ultimately end up producing ionizing radiation. Ionizing radiation, when it hits atoms, causes them to shed electrons, right? And as they shed electrons, that's why it's called ionizing radiation. It could cause damage to biological material, especially to DNA. And when we damage DNA, what typically will happen is the cell will either go out of control. Usually the DNA are the instructions for life, which means the cell usually dies, or the cell gets out of control, right? And we know what that means. Right? So there's a number of different scenarios here where gamma radiation or other types of emissions will lead to radiation that can be dangerous for biological organisms. So when we think about the hazards working with radioactivity and the dangers of radioactive emissions and the damage from radioactive sources, it all comes back to these to radiation. It comes back to the emissions of energy, and as the photons of energy reach living cells, they have the ability of penetrating living cells. And again, the textbook gets a little bit into what happens when penetrating radiation hits biological material. And again, I'm going to leave that for you to read if you are interested in that. Okay, so there's some examples here that I've included in my note. This is the note that's on the hub. So again, work on these 3 questions here. In our textbook, there are some questions on page 640, and there's a few more questions on 663. And that's definitely the most out there note of our entire semester. But as you take more and more physics, just like as you take more and more math, and you think, wow, I had no concept of that ever happening. Physics is going to take you some of those places too, which is why physics can be terrifically interesting. Mind you, I'm kind of biased, so. All right, so I will leave you with all of that, and I will talk to you soon. I encourage you to stay on top of the calendar in the hub. I would check it daily because I'm slightly changing things as we're moving through. We've got another, so you've got the OPG assignment that you were working on. Hopefully that's done. You were working on, there's another gizmo that's coming up on decay and half-life, and that will be coming up in a couple of days, either tomorrow or the day after. And then there's a movie I want you to watch, a video I want you to watch online about nuclear medicine, which has got basically almost nothing to do with what we're doing in this course. But I think it's where a lot of biology meets physics, and a lot of you are taking biology and interested in biology, and biophysics is a huge, huge area, and using physics for biological applications, we're going to see becomes more and more and more a part of where medicine and recovery and therapy is going. So, I think that's it. Yes. So I will leave you with that. So again, check your calendar. Again, remember we're doing both the tests together for thermal energy and for nuclear energy together next week. Again, the dates are all on the calendar, so just stay on top of those dates. And if you have any questions, reach out and let me know. If you were looking for the online class this morning, which was Tuesday morning, I was the only one in there, so there was nothing to record.